All right, so today we're in section 7.8. This is the last section in chapter 7, and we're dealing with the topic of improper integrals. So up until this point, we've dealt with two different types of integrals. We've dealt with indefinite integrals, which really is just antiderivatives, finding the antiderivative of a function. And then we've dealt with definite integrals, where we use that antiderivative, but what we're really finding is the area under a curve over some finite interval a, b. However, there are certain applications of integrals where we need to integrate a function over an interval that's not finite. So something that looks like negative infinity to a, or a to infinity, or even negative infinity to positive infinity. This is sometimes called integrating over the real line. So those particular types of integrals we haven't dealt with yet. We haven't talked about how to deal with infinity showing up in one of your limits of integration. Another type of integral that we haven't really been able to deal with yet is when you want to integrate a function, when you want to find the area beneath a curve over a finite interval, but where there's an infinite discontinuity of that function somewhere on that interval. So an infinite discontinuity means graphically you're going to have a vertical asymptote. In those sorts of cases, can we end up with a definite integral that you can evaluate that represents some actual finite area? And the answer is that it kind of depends on the function and what's going on there. So we're going to look at that today. Those integrals, the types where we're either integrating over some infinite interval like this, or if we're integrating over a finite interval that contains a vertical asymptote, those are called improper integrals. And that's what we're dealing with. We're going to categorize them into those two types. So the first type we're looking at is if you want to integrate a function over an infinite interval. Okay, so let's take a look at an example here. Suppose for a second that we wanted to determine the area under the curve f of x equals 1 over x squared. That should be squared there, just a typo, to the right of x equals 1. Graphically, this is what that region would look like. So here's the part of the curve f of x equals 1 over x squared that contains the region that we're looking at. Everything to the right of x equals 1, we're accumulating area under this curve. Now, because the region goes infinitely towards the right, this area is going to continue accumulating indefinitely as we continue approaching this horizontal asymptote at the x-axis here. So it's tempting to look at that and think, okay, because this region extends infinitely to the right, the area under this curve must be infinite. However, we're seeing that as you approach, I was about to say, as you approach infinity, you can't really approach infinity, but as you continue further and further to the right, the amount of area that's being accumulated gets really, 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 really small. And in fact, it turns out that for this particular function, the curve is approaching that horizontal asymptote fast enough that this region ends up having a finite area instead of an infinite area, which you might expect to happen. So we haven't shown why that's the case yet, but we're going to in a minute. Let's think about how we might try to approximate that area if we didn't know what else to do. So I can think of this integral as the integral of 1 over x squared dx, and my limits of integration as going from 1 to infinity. I can think of the upper limit of integration as being infinity, since this goes forever to the right. Now, infinity is technically not really a number, so you can't just plug infinity into something. So instead, let's imagine our integral is looking like this. The integral from 1 to t of 1 over x dx, but we imagine t to be a very, very large number, so that we can kind of get an idea of what's happening with that area. This is an easy integral to evaluate. Its antiderivative is negative 1 over x, and our limits of integration are going from 1 to t. And if I plug t and 1 into this and kind of rearrange some terms, this is equal to 1 minus 1 over t. Now what I would do is think what's going to happen to this expression, which represents the area under that curve. What happens to this expression as t gets larger and larger? So here are some examples. If t is equal to 2, that's 1 minus 1/2, which is 1/2. That's what the area would be. If I have t equals 3, 1 minus 1/3 is 2/3. So the area from 1 to 3 is going to be 2/3. And you can continue kind of doing that, right? But maybe you're seeing where we're going with this. If I'm imagining t as being very, very large, one way of thinking about that is letting t approach infinity. So instead of just plugging numbers into this, we could also take the limit as t approaches infinity to see what happens to this expression. That's what we're doing right here. So we're going to take the limit as t approaches infinity of this original integral, which is the same thing as applying that limit to this expression. And I can see that 1 over t goes to 0 as t goes to infinity, which means this goes to just 1. So that tells me that this area, again, even though this area extends infinitely towards the right, the actual amount of area in the blue region is numerically equal to 1. Okay? Notationally, we represent that type of an integral where I had to take a limit as my upper limit of integration went to infinity. This way, the integral from a to infinity of f of x dx, even though infinity is not actually a number and you can't plug it into an expression the way you can some other real number, we still use this notation to mean this. So when you see that infinity there, really what we're thinking of that as is a t there, which we then take the limit as t approaches infinity. Okay, so that's one of these type 1 types of improper integrals, and really there's 3 different categories that these type 1s can fall under. We can have integrals of this type, where our limits of integration go from a to infinity. That's what we just discussed here. Here's what it would look like with the limit. We can have integrals of this type, where we're going from negative infinity to some finite number b. And that is going to be defined in a similar way. We replace that negative infinity with a t, and then I take the limit as t approaches negative infinity. So that is defined to mean this. Then the third case that we could think of is if we want to integrate a function over the entire real line. So we're looking at integrals that take this form, the integral from negative infinity to positive infinity of f of x dx. The way that we think about this is we pick some number, some real number between negative infinity and infinity, which would just literally be any real number. And we use that to split this into 2 separate integrals. So for example, if that number is a, whatever a happens to be, I could take this integral and split it up into 2 parts. Negative infinity to a is my first interval, and then a to infinity would make up the other interval, which together gives me the entire real line. So if I'm able to split this thing up into a sum of 2 integrals of these types, which notice those are like types A and B in our table up here, and then if it also happens that each of these integrals gives me a finite area, then I define this integral to be the sum of those 2 finite areas. Now there's an important term or pair of terms that we use for integrals of this type. So if you remember from Calculus 1, when you first learn about taking limits as something approaches infinity, there are lots of cases where those limits fail to exist, either because they go to infinity or they have some kind of oscillating discontinuity or something like that. Or not discontinuity, but some sort of like oscillating behavior. If this integral leads to a limit like this and that limit does not exist, we say that the improper integral is divergent. But if it does exist, like in the case on the previous page where we found that improper integral of 1 over x squared, dx, and we found that the solution was 1, then we say that those improper integrals are convergent. So again, improper integrals, if they give you a finite value when you apply that limit, we say that the integral is convergent. Otherwise, if the limit does not exist, we say that it's divergent. Okay? let's take a look at an example. So I would like to determine if this integral going from 1 to infinity of 1 over x dx is convergent or divergent. So the first thing I want to do is rewrite that integral as a limit. And I'm going to replace the infinity here with the t that I'm using there, 1 over x dx. All right, this limit, as t goes to infinity, I'm going to be taking the limit of this, which is the natural log of the absolute value of x from 1 to t. The absolute value is unnecessary, really, because the limits of integration are all positive here. Okay, that is the same thing as the limit as t approaches infinity of the natural log of t minus the natural log of 1. Of course, the natural log of 1 is equal to 0, so really this is just the limit as t approaches infinity of the natural log of t, but that is an infinite limit. So that goes off to infinity. It doesn't have any horizontal asymptote or anything like that. So that means that this integral is divergent, because it did not give me a finite area. It did give me a finite solution. The limit does not exist. Okay? So that's all we have to do for that one. Let's try another one. I want to evaluate this integral, the integral from negative infinity this time to 0 of x e to the 2x dx, if it's convergent. If it's not, I would like to show that it's divergent, which would follow a similar procedure as this. So same idea, but what I want to do, I want to find the limit as t approaches negative infinity this time, where I'm going to replace this negative infinity with that t of x e to the 2x dx. Now this type of integral, I would need to use integration by parts to solve it, so I'm going to do that next. Over here to the side, I'm going to let u equal x, and I'm going to let dv equal e to the 2x dx. So that du is dx, and v is 1/2 e to the 2x. So now, using integration by parts, this would be the same thing as uv, so I could write that as 1/2 x e to the 2x, that's uv there. And again, remember, I'm evaluating that from t to 0, and I almost forgot to include my limit here. Limit as t goes to negative infinity. Don't forget about your limit, because that's going to be applied to that t right there. Okay? Then I'm going to subtract, and I know what's coming here is going to be another integral, but it's going to involve that t, so let's make sure that we include that limit as t approaches negative infinity in there as well. My integral is going to go, but the integrand is going to be v du. I do see a 1/2 there, which I can not only bring outside of the integral, but I can also bring outside of the limit that appears here, because we know that that's a property with limits that we get to use. Now we're going from t to 0 of v du, so that's e to the 2x dx. The 1/2 I've already dealt with over here. All right, now let's work some of this stuff out. So here I have the limit as t approaches negative infinity, and I'm going to plug a 0 in for this. It's going to go to 0, and then if I plug a t in for this, I get 0 minus 1/2 t e to the 2t. Okay, so let's leave that there for a minute. And then here, I can evaluate that integral, so I have minus 1/2 times the limit as t approaches negative infinity. This is a fairly easy integral to evaluate. It's just 1/2 e to the 2x evaluated from t to 0. All right, so I have a couple of things to work on here. This integral, or I'm sorry, this limit is an indeterminate form, because if I look at where t is approaching, negative infinity, as t approaches negative infinity, this factor right here is going to negative infinity. As e to the 2t, if I let t approach negative infinity, this guy goes to 0. So it's an indeterminate form of the infinity times 0 form. That means I can use L'Hopital's rule to evaluate this limit. But before I can do that, I would have to write it slightly differently. Let me pull the 1/2 out, the negative 1/2 out. Limit as t approaches negative infinity. I'm going to rewrite this as t over e to the negative 2t. Okay? So this is the same thing as this, and there's where the negative 1/2 went. Over here, I can do something kind of similar. Let me bring this 1/2 out, multiply it to that 1/2 to make 1/4, minus 1/4. And then I'm going to have the limit as t approaches negative infinity of e to the 2 times 0, which is just e to the 0, or 1, minus e to the 2t. Okay? Let's think about what this looks like if I apply L'Hopital's rule, because now this is an infinity over infinity type of indeterminate form. That's negative 1/2 times the limit as t approaches negative infinity. L'Hopital's rule says I can take the derivative of my numerator and denominator if this is an indeterminate form. So derivative of t is just 1. Derivative of this would be negative 2e to the negative 2t. And then here I'm going to have minus 1/4 times. So I have 1 minus, as t approaches negative infinity, this exponential is going to shrink down to 0. So this becomes 1/4 times 1 minus 0, or 1/4 times 1, or just 1/4. Okay, finally, looking at this last term right here, as t approaches negative infinity, here's the only t that's left in this expression. I already have a negative 2 in front of it. So negative 2 times a negative number here would be a positive number. And as that number gets larger and larger, like going towards infinity, my denominator is getting larger and larger. I'm multiplying it by a negative 2, so it's actually getting smaller and smaller in the sense of going towards negative infinity. But regardless, 1 over that number that has a very large absolute value would be the same thing as 0. So this whole limit here is going to go to 0, and what I'm left with is that negative 1/4 right there. Okay? That is the value of that improper integral. Now, if you're going through this section and you're wanting to do a sanity check, which I believe we've talked about sanity checks in this section, or in this class before. A sanity check is a quick way of determining whether or not your answer makes sense. Sometimes you can put a lot of work into a problem, get to an answer, and not be completely sure if you have the correct answer. If your answer is, violating some kind of common sense thing having to do with that problem, then it's a quick way for you to determine that something might have gone wrong. So for this, if you were to graph the function x e to the 2x using a graphing calculator or Desmos or something like that, and look specifically at the part of that function that goes from 0 to negative infinity, so everything to the left of the y-axis basically, you would see that this function is completely below the x-axis, which means all of that area would be counted as negative. So it is correct that we're getting a negative value here. Secondly, you would see that there's not very much area there. It kind of dips down below the x-axis, but then it very quickly starts approaching the x-axis again because there's a horizontal asymptote as you go towards negative infinity. So that means there's not a whole lot of area. Negative 1/4 feels like a reasonable answer when you compare it to what the graph of this thing looks like. Okay? Let's take a look at another problem. Juggle my notes around here. There we go. This time we're going to deal with an integral of the type negative infinity to infinity. So we're integrating this over the entire real line. There is an alternative notation which you won't see very much in this class, but you may see in other classes, and I just want to mention it because it's, it's worth knowing what this is if you ever come across it. Sometimes we can replace this negative infinity to infinity with this symbol right here. This is a text, it's called a blackboard bold R. And what that is the symbol that represents the set of real numbers, which the interval negative infinity to infinity is just another way of saying the set of real numbers. So this notation is sometimes used in place of this. That's just a side note. So let's see if we can evaluate this now. The way that we're supposed to be dealing with improper integrals of this type is we pick a number, some real number, and we split this up using that number into two separate improper integrals, which we then add together if both of those are convergent. So to me, the number that makes the most sense to use is 0, which means we want to look at this integral here, and this integral here. Okay? If both of these are convergent, then I can add them together to get this integral, and that would be my answer. So my goal is to show that they're convergent and also what they're equal to. To pull this off, I need a u substitution. So I'm going to write off to the side here. I'm going to let, in both of these integrals, u is going to equal negative x squared, so that du is equal to negative 2x dx. And solving for the x dx, since I have that in my integrand, I have negative 1/2 du equals x dx, okay? So I'm going to use that in a second, but let's first set this up using the limit. This is going to be a limit as t approaches infinity of the integral from 0 to t of x e to the negative x squared dx. Okay, now we make a u substitution. So that means that this limit is going to be a limit involving a u instead of a t. Now come over here for a second. If t is approaching, let me back this up. I'm going to leave the limit alone. I'm going to handle this in a slightly different way than I was initially thinking. Okay. So our limits of integration here are going to be thought of as x values, but we have to plug them in here to get corresponding u values. If I plug a 0 into this, I still get a 0. If I plug a t into this, I get negative t squared. This is now negative t squared. Okay, that's the way I want to approach that. My new integrand here is going to look like e to the u du. That's the substitutions that I just made. Okay, this is the same thing as the limit as t approaches infinity of e to the u, where we go from 0 to negative t squared, which is the same thing as the limit as t approaches infinity of e to the negative t squared minus e to the 0, which is the same thing as 1. Okay? Now, as t approaches infinity, t squared is still approaching infinity, but then putting a negative out front means this is going towards negative infinity. And as this exponent goes towards negative infinity, e to that power is approaching 0. So this is going to go towards negative 1. Okay? That's what's happening there. Well, I think this one was supposed to come out to a positive 1. So something about... I see what went wrong. I made a little mistake here. I forgot that it's negative 1/2 du. I do need a negative 1/2 there. Let me include that everywhere. There should be a negative 1/2 there. So this becomes negative 1 times negative 1/2, which is equal to 1/2. I was going to say, because to the right of the y-axis, this function is positive, so I shouldn't be getting negative area. That wouldn't make any sense. So that first integral gives me a finite value, 1/2. Okay, I can follow a similar procedure for this second integral here. So t is now approaching negative infinity, and there's where the t goes, 0 x e to the negative x squared dx, making my u substitution. And this time I don't want to forget to include that negative 1/2 there. This is equal to negative 1/2, limit as t approaches infinity of... Now, remember, these new limits of integration have to be u values. So when I plug a t in, I get negative t squared down there. And I still have 0 up there. This becomes e to the u du. Notice it's very similar to what we did up above. The only difference now is these limits of integration. Now, I could continue kind of working through this the way that I did before, but you may notice that this integral is the same thing as this one, but with the limits of integration reversed. And we already know what happens when you do that to a definite integral. You get the opposite of what you got previously. So that's going to be something that we can use to shorten up the work. Where I got 1/2 before, I'm now going to get a negative 1/2. Okay, so since I got finite values for both integrals, that tells me that the integral from negative infinity to positive infinity of x e to the negative x squared dx is just the sum of these two. It's equal to 1/2 plus negative 1/2, or 0. So we end up with an integral of 0 in this case. It's convergent, but it's equal to 0. All right, let's end this one here. We're going to keep going with more examples in the next video.